My name is William, and I work at emqx. And for your information, emqx is open source MQTT broker, written in Erlang, of course. Today, in this talk, I will cover two topics. First, I will give you some general introduction about what is QUIC, the history, the function it provides, and in which field you might use it. And the second part, we will talk about the experience of building a QUICER library, which is for OTP Beam. OK, first glance of QUIC. QUIC is the new transport of HTTP 3. And it is UDP-based, but it is connection-oriented. It provides multiplexing with streams, and it has a lot of features for the streams, like flow control. And it is end-to-end encryption. It has embedded TLS 1.3 for handshake, but the frames, it's QUIC frames for data transfer. So who use QUIC? As you can see, the large players or the vendors, they all adopt QUIC. And cur, our favorite command tool, also support HTTP 3 now. So it's kind of in production. Some history about QUIC. There are two terms. First is GQUIC. GQUIC is initially written by Google since 2014. And it's mainly used for the traffic between Chrome browser and the Google service, such like YouTube. And in 2016, QUIC is already becomes like 35% of Google egress traffic and 7% of the whole internet traffic. And in 2016, same year, Google bought this to IETF to make it world standard, to make it standardized and modularized. So why QUIC? Before speak of that, we try to revisit what is HTTP 2. So above IP, we have TCP, which is very reliable transport. It ensures in-order delivery, and it do congestion controls and loose recovery. And on top of it, we have TLS 1.2, and it is trusted, encrypted section. So nowadays, data is privacy, so encryption is kind of mandatory. Then on top of this, we have the application, HTTP 2, which compares to HTTP 1. It provides multiplexing with streams. So with streams, you have parallelization. For example, you can when you are in the browser, the browser can fetch the resource in parallel, like HTML page, JavaScript, and CSS files. Also, it provides priorities. So when you open a web page, some pictures is having higher priority because it is in-screen image, and then it can down prioritize some image which is off-screen image, such like when you scroll down, the image will show up. Yeah, and flow control is another consequence of providing multi-string. So presumably, if everything works like this, each endpoints just talk like on each layer, which works perfect. But what if we have some more evolutions, try to, for example, improve the TCP congestion control? There is a problem called the middle box problem. Middle box problem is kind of very famous when we talk about QUIC or networking. So what is middle box? They are not routers, like the routers at your home. It's do network address translation, because we have very limited IPv4 addresses. And we have firewall. They provide the security and access control, and we have a load balancer that your request is load balanced to different backend server. The problem of middlebox is that they have no idea about up layer, but they try to do some smart things. They try to guess what it is and try to block or do some weird stuff. And some of them, they are actually transport endpoints. So when you think you are talking to the server directly, but actually you are talking to the load balancer, and there are two endpoints. And those we have lots of middlebox, and the one single vendor has no control. And so that is deploying new features is almost impossible onto those middlebox when it comes to new standard. And even when deploying TLS 1.3, there is called a middlebox compatibility mode. That is TLS 1.3 tries to pretend it is TLS 1.2 and try to pass through all the middlebox. So that is why QUIC is on UDP. UDP is existing protocol, and it's like everyone supports it, and it's the minimum requirement to run the new protocol. And also QUIC built on top of UDP, then QUIC has all the features implementations I talk about at the left side. As one big point is that it brings down the streaming multiplexing from application layer to transport layer, because this is actually the work transport layer should do. Okay, one problem QUIC solve is that the performance of handshake. Let's see how TLS over TCP do handshake. First, we do TCP handshake, and I draw the red blocking points. That means the endpoint in this picture is client is blocked, and it can do nothing until it's received the response from remote. And after TCP handshake, we start TLS handshake, and only after TLS handshake, then we can start exchange application data. As you can see, we have 3 blocking points. That is sort of 3 round trip needed to finish handshake. QUIC solve it, call it one RTT, one return chip. So because QUIC runs over UDP, there's no need to initialize a connection or do handshake on UDP. Then in terms of TLS handshake, both client and server, they try to guess the most popular or algorithm for key exchange. So the client do not need to wait for server to select the algorithm. That speed up a bit, so that's why we have only one blocking point. After handshake, of course, we have application data exchange. Next problem QUIC solve is reconnect issue. Reconnect is very common. Like the client stays in a loosey network on a very fast-moving object, like on a train. And clients, they can switch in networks, like you go out of your home, you switch from Wi-Fi and switch to 4G network, meaning the IP address is changing. In that case, there will be like reconnect. And the clients can also sleeping when you hibernate your laptop. The connection is kind of closed. And when the service provider is doing server-side maintenance, providing new features or patching, they are called occurs massive reconnects. Reconnects are very expensive because the handshake is slow. The most CPU usage during TLS handshake is actually on the handshake part. And it is also very many bytes transport on transport layer. And also it creates extra overhead on the application layer, because in application, mostly they have a status, and disconnect, reconnect is shifting status. And for massive reconnects, to some service, it's like DDoS, and you can't handle it well, and it's really hard to test the ceiling. QUIC solve it with two features. The first is zero RTT. As I showed you before, after client and server, they have finished one RTT handshake, start to exchange application data. The server can send a new session ticket to the client. This is a re-entering ticket, so client can just remember the ticket. If the connection is disconnected due to idling or something, client can just reuse this session ticket, and especially in the first message sent, it can contain the early data, application data. So they call it zero RTT because there's no handshake, no blocking needed. Oh, sorry. This is, we call it connection resume, but in QUIC protocol, it's actually a new connection just with older session ticket. Yeah, QUIC solved the connection issue also with this connection migration. Here I will talk about the active migration. Because in TCP and UDP, you identify the pair with 5 elements tuple, as I show you, the addresses, ports, destination, source, and the protocol, UDP or TCP. But in QUIC, we use connection ID. Yeah. At the right side, I just give you an example. If your client is using Wi-Fi as your access network, talk to the server. With QUIC, you can also probe with another network. The probe means that we are like testing the network path if it works okay, and also the MTU size if it can work with the UDP. Yeah. For example, if once we have some conditions at Wi-Fi network, the client can just switch to use 4G network. In this case, the IP address is changed, but the connection ID is not changed. So to host and the client, it's just a very smooth migrate. And sorry, this is active migrate. We also have unintended migrate, which is like similar. Okay, QUIC also try to solve the head offline blocking issue. Let me explain what is head offline blocking issue. Imagine that we have a TCP connection, and in this TCP connection, we have 4 HTTP2 streams. They all send in like this order, and in this picture, I color the frames with different colors, and you can see it. But to TCP, TCP is kind of blind to these colors. It doesn't know what are they, and since TCP has the nature of ordering delivery, once one packet or one frame is lost, it blocks the entire connection, especially when you can't recover it or something. Because TCP also having issue try to recognize if it's lost or not. Yeah, before I talk about how QUIC solve it, I can have a short conversation about how QUIC packet the entire data. So the outer box, we have a UDP packet. It can have multiple QUIC packets. And in one QUIC packet, it has headers having like destination connection ID and the packet number. And in the first packet I show you, it has 4 frames, 2 frames. They are stream frames for carrying application data, and the third frame is for echoing the response, and the 4th frame is for TLS handshake, like sending the returning ticket. Yeah, so I just converted from TCP to QUIC. You can see that we have 4 streams sent in parallel. And let's talk about what is streams in QUIC. Yeah, they can share the same connection, and we have bidirectional streams and unidirectional streams, so that the streams can be initialized from client or from server for like server push. And the ordering is guaranteed per stream. So, and the frames between different streams then can overrun. Yeah, and we have flow control. Flow control can be on both stream and the connection level. Now, stream is like counting the bytes, and the connection you can connect. I think, yeah, you can count the number of streams. Back to the packet lost. Let's say if we, in this red one, let's say we lost packet number 100. It will only block string 1 and string 2. And the rest, string 3 and string 4, they can continue proceed. Yeah, QUIC is also built for agility because nowadays service provider care about quality of experience, not only quality of service. So quality of experience is like, on a video call, can you see me? Can you hear me? Yeah, it's like end to end. And service provider want to control, and they want deploy new features, bugs fixes, security patching more easily, and they want to involve some architecture innovations like direct server response or something. So life will be much easier in user space. So QUIC is mostly designed or developed in user space instead of kernel space, because if you deploy user space, you don't need to redeploy the kernel or recompile the kernel module. That is the one reason why QUIC went alive so quickly by all those companies before RFC is finalized. That's all about QUIC. Now let's move to QUICER. QUICER is library for Beam, and it's actually NIF wrapper, the MSQuick library written by Microsoft. QUICER is very thin layer wrapper, and it is libraries out of OTP because of agility. There are some design decisions I can share. We are still rapidly changing the code, but some design decisions still will stay there. First, it's like we want to provide a similar API or the behavior that can, like Gen Server, Gen TCP, and SSL, so that you can easily migrate to use QUIC, and it provides the sync and async API variances, because the whole thing is built on top of asynchronous core. I will show you later. And it also supports active passive receive mode, and also for the process owner of the stream or connection, you can switch it with some API. And last one, we have also automatic resource cleanup, like if the process is dead, the connection or the stream can be closed. Okay, my colleague suggests me to give you an example of ping pong, so I will go through it quickly. First, you need to start the QUICER application. This will initialize the MSQuick library. Then you can start a server listener. Then you get the listener handler. Then you can accept on the listener handler. Then once the connection is incoming, you get the connection handler. Then you switch to handshake if you want to accept that, if you want to continue handle this connection. After connection is established with connection handler, you can accept the new streams on that. If the client side initiate the new streams, you will get a notification, and you will get a stream handler. Then you get quick messages from remote, just like this. And then you can send a POM message and close the listener. Client side is similar. We have, after start a QUICER application, you connect with some parameters. After connection is success, you start connection on. You started the stream over this connection. Then you can send some data over this stream. Then you can also receive data in your mailbox and close the connection. Okay, so then let's talk about how MSQuick interwork with Erlang. So we have 3 boxes here. The outer one, the red one, is Beam process. Okay, the Linux Beam process. And inside we focus on 2 threads. The blue one is scheduler thread, And the yellow one is emqx worker, and this thread owns by Microsoft, emqx. So we started, but we don't. We just provide callbacks. And the QUICER NIF code is separated into two parts. One is called the NIF context, that is the code is used in scheduler, and another part is that they are the callback functions that will be used by emqx worker. And emqx worker just do two things, simple things. It interacts with network queue. You see the green arrows, and also it work with a work queue, that is either you submit the work from Erlang schedulers or the work from another emqx worker. Yeah, and in the Erlang scheduler, when you're calling those NIF functions, they are actually just shoot asynchronous tasks into the work queue. So this call is kind of very light, and it's asynchronous. And after the worker has done the work, then call our callback, and then our callback will just shoot message back or shoot the result to you. That's it. Yeah, in QUICER we are really focusing on troubleshooting. So you can debug with Wireshark, and QUICER support that you can specify which connection you want to export the master key of SSL, TLS, and then you can decrypt your entire capture of Wireshark. And we also very serious about tracing. We use LTTNG tracing. I think this is the best fit because both Erlang Beam VM and emqx, they support LTTNG. And also we wrote some LTTNG agent for low-level, high-performance tracing. Yeah. Okay, current status of QUIC. It's still in proof of concept because lots of things are changing, and we are still learning how to do it in NIF. It supports lots of platforms OS as usual, and we have verified the traceability, so we can start more massive development. And for the testing, we think because of those threadings, parallel things, we use Snap Cafe, which is trace-based testing together with common test, so we can very carefully check what is going on inside. And we did some simple performance tests, and we didn't find any big surprise. And we use CodeQL to scan the security and some best practice of C. And we're also using memory error detector. We learned it from OTP. Next, yeah, QUICER is still very young. It was postponed for a few months, and now we have customer interested in it, and we aim to improve it by configuration, because current configuration are mostly default or hard-coded, and we want to improve or write some documents for that. And yeah, of course, improve coverage in the common tests. And we are aiming for production grade by the end of this year. This is our goal. Yeah, I think that's it.